In this problem, we'll construct a quantitative motion map in 2 dimensions. Assume a ball rolls on a 45-meter high horizontal platform with an initial speed of 10 meters per second. At the same instant that the ball rolls off the edge, an identical second ball initially at rest is going to be released at the platform's edge. You can use g equals 10 meters per second squared for this investigation. That's an approximation of 9.8, but it makes the math a little easier. Complete the tables below and then find the time of flight for both balls. As we can see in their initial positions here, one of the balls has a velocity vector attached to it and the other doesn't. So ball A here is going to start from rest, whereas ball B is going to be moving. Notice that they're both dropped from 45 meters above ground. So let's go ahead and put in their initial coordinates right off the bat. Both the balls start at an x of 0. And they both have a y of 45. Now one of these balls is not going to move in the horizontal direction at all. It's only going to move vertically. That would be ball A. So knowing that, I can plug in that after 1 second, it's still located at an x of 0, and after 2 seconds, it's at an x of 0. It stays at an x of 0 throughout time. Ball B doesn't, though. Ball B is moving horizontally with an initial speed of 10 meters per second in the I direction. Now, as I discussed in a previous video, Earth cannot change the horizontal velocity of an object because Earth only pulls down, and the x and y components are independent. What this means is that after 1 second, we'll find that ball B has moved 10 meters. After 2 seconds have passed, it'll be at the 20-meter mark, and then after 3 seconds, it'll be at the 30-meter mark. The formula I'm using for that is delta x equals Vx times t. All I have to do is plug in the horizontal speed of ball B and multiply that by the elapsed time. That's how I found these values. So for any projectile problem, when we're dealing with the horizontal dimension, we want to use this constant velocity formula. It's not accelerating in the x dimension. However, the balls are both going to be accelerating in the y dimension. So in order to find y positions for the balls, we have to use a formula which involves acceleration. The formula to use will be this: y equals 1/2 ay t squared plus viyt plus yi. It's a formula that's been derived for constant acceleration. Now the acceleration we'll use will be -10. It's negative because Earth pulls down. So we'll do this. Y equals 1/2 -10 t squared. We're going to have 0 initial velocity for ball A because it starts off at rest. And let's give it a yi of 45 according to the picture. All right, if we simplify that a little, we get negative 5t squared plus 45. When t is 1, our ball will be located at a height of 40. When t is 2, our ball will be located at a height of 25. And then when t is 3, will be located at a height of 0. So now we can go ahead and plot that motion map for the dropped ball. It's located here at t equals 1, 25 for t equals 2, and then just about 0 at t is approximately 3. All right, now I also want to draw velocity vectors. And I could just do them as we've done in the past, just as a qualitative sketch. But I think what I'll do here is I'll actually calculate what the velocity of the ball will be throughout time. How do we do it? We can use this formula, v final y equals ayt plus v initial y. All right, so let's plug in our acceleration, negative 10. And our initial velocity for ball A, of course, is 0. So we get negative 10t. This means after 1 second, our ball will be moving with 10 meters per second in the downward direction. So I can draw this. After 2 seconds, we'll be going 20 meters per second in the downward direction. And then right before we impact ground, we'll be going at 30 meters per second. All right, now what will happen with ball B? All right, so for ball B's vertical positions, we want to use that same formula, y equals 1/2 ayt squared plus viyt plus yi. The acceleration that B feels will be the same as what A felt. And now what about viyt? This is an issue that a lot of people make a mistake on. Sometimes people will look at ball B and see that it's moving with 10 meters per second, and they may want to plug that in here. But you can't. You can't because that is a horizontal component of velocity. This velocity is completely in the horizontal dimension. It's not in the y dimension, so it has no impact on formulas that are about the y dimension. The ball is neither moving up nor down at the start as it rolls off that table. And for that reason, we have to put a 0 here. It's one of the most common mistakes. Now our yi will be 45, and as we can see, according to the formulas, the equation for where ball B is located is the same as the equation for where ball A would be located. So we have the same elevations at these different times. What does that mean? It means the balls will fall side by side. and they will hit ground at the same time. Okay, we can sketch the path. Now we'd like to draw velocity vectors if we can. I'm going to start with components. I know that the horizontal component will remain the same throughout time. It won't change. It'll stay 10 meters per second all the way down. But when it comes to ball B's vertical velocity, it will actually follow the same formula here that A had followed. This is for the y component of velocity, and so these are going to match. What we can do now is we can draw what is called the total velocity. So this is VBX. This is VBY. And when we put them two together through vector addition, we get the total velocity. Interestingly, the total velocity here will remain tangent to the path of the object because it shows which way the object is traveling. As you can see, the speed of the object is getting larger and larger as time goes on. Lastly, we're asked to find the magnitude and direction of each ball's total velocity just before impact. Well, I can already answer that for ball A. I said that if I plug in a time of 3 here, then negative 10 times 3 would give me 30, and that's going to be the magnitude of this final vector. So VA final equals negative 30 in the j hat direction. So its magnitude and the direction is 270 degrees counterclockwise from the positive x. Now calculating the magnitude of ball B's velocity is a little bit tougher. First, we're going to want to identify its components. So VB final in the x dimension is going to be the same as VBX was initially. It's 10 meters per second in the I direction. But VB final in the y direction will be negative 30 meters per second in the j hat direction. Negative 30 meters per second j hat. Now I just want to find the length of that total velocity vector. That is the length of VB final. How long is it? Let's use the magnitude formula. It's going to be the square root of 10 squared plus negative 30 squared. .6 meters per second. And then let's find an angle for it. First I'll find my reference angle. It's the tan inverse of 30 over 10. (71.6 degrees). That, of course, is going to be the angle between the x direction and the vector. So to get my standard position angle, since we're pointing toward the fourth quadrant, let's do 360 minus beta. (288 degrees).